embedded communication protocol. But typically embedded communication protocol means few typical rules we have to design, we have to set aside. Following them, we can achieve few requirements, we can satisfy few requirements so that two independent embedded systems can communicate to each other. Okay. Oh, 1 second. Let me check whether the recording is started. Yes. So for that, so now it is clear why heterogeneity it is important to handle. We have seen in a small domain, small automobile domain, there are too many diversity. Why we are going to choose different types of embedded system, embedded components. So we have to we have to communicate within typical diverse scenario. Next one, which language to talk. That means whenever, okay, this point I will come later. I mean, we will go in detail. Next, finding the best real-time protocol. Real-time protocol means you understand that whenever we are considering any embedded system, cyber physical system, where embedded system is the main pillar, what we have to consider that there is a typical task given to that particular cyber physical system. So that real-time requirement, the task deadline, that needs to be met. So this is a challenge, that how we can get that best real-time protocol. Then this part, collision handling in media access, I will come again in detail. Every point actually we will go in detail, then I think it will be clear. Then error detection. Error detection means, as you can understand, that communication means in layman's term that some data you are sending from some sender to receiver. Now in between path, it may happen there are some issues, there are some overlaps, some signal intrusion. There may be many reasons. For that, the data you are sending, you have to there should be some guarantee that whatever you are sending, your receiver is actually receiving the same. So what are the mathematical ways, what are the typical ways by which the receiver will actually get the knowledge that whatever data the receiver is actually receiving, it is exactly the same what is sent from the sender. So there are a few error detection algorithms that we will mention a bit maybe in this course. And the security in some distributed scenario, like when you are sending data from the sender to receiver, what is the guarantee that someone in between, some man in the middle, is not changing your data, or it is not whatever data you are getting, you are thinking you are getting that from a particular source, but actually maybe that source is inactive, or that source is maybe compromised by some adversary, and you are receiving whatever data you are receiving from some maybe some adversarial node. Now this is a quite advanced topic, so we do not discuss this in this course, or in embedded networking course also. There is a separate course for that where we discuss that is the security aware CPS and IoT design. There we discuss such topics. But here I will try to give, in this fundamental part, I will try to give some idea about how we are actually handling in embedded communication scenario these few topics. So first, very basic point, what are the types of embedded communication we are actually going to handle? There are two particular types. One is point to point. That means the nodes are connected point to point. Each node is connected to every node, and there is some communication requirement that we have to handle. What is the advantage? The advantage of implementing these type of communication is that is simple and of course reliable. Compared to the other form, what is called shared media network. Shared media means there is one typical medium that is shared by multiple nodes. So the advantage is, of course, that you are reducing the varying cost, but you are compromising with your reliability. That means the communication, whatever you are proposing here, is not quite dedicated. So actually, we will take example of one by one, I mean each of them. Today we will discuss about CAN. There you will see what is the concept of shared medium and how we are, how multiple nodes are communicating through that. And maybe next day, Monday, we will talk about some dedicated communication. So other than this, the other type of classification which is relevant in embedded domain, that is even and state based. That I hope by now, whatever we have discussed in our so-called, I mean, modeling techniques, now you have some idea that in real-time scenario or in general embedded system, general CPS system, there are two types of possible communications. One is some event is occurring, maybe that event is generating from some sensor input, some other any kind of trigger that is generating the event, and based on that event, some communication should be taking place. Other one is state based. State based means those are very, maybe we can say that is the message representing the interstate of the node, and those are very fixed size and regular. So that means whenever we are talking about event driven communication, event based communication, there is some amount of irregularity. So, some amount of sudden events are related. But whereas state-based communication we are talking about, they are fixed size and predefined. And that is the main challenge in embedded design or embedded communication design, that you have to consider both the things, event-driven messages, event-driven communication, as well as state-based messages or state-driven communication. Okay, so that is the main challenge in case of finding the real-time protocol in embedded scenario, that there is a fundamental conflict. Because when you are thinking of event-based system, remember when we talked about the modeling scenario, for event-based system, this is not required that whatever communication strategy you are taking, that should be established. The communication between sender to receiver should be established, and you have to maintain that throughout, I mean all the time. That is not required. But what is required, that whenever the event will occur, immediately the communication should be established, and there should be a particular session or particular time the communication should be maintained. So that gives some amount of efficiency or flexibility. Whereas if we are considering state-driven scenario, there you have something regular. So some regular communication channel, regular communication process, some protocol should be established. But both should go together. And that is, I mean, somewhere if you are supporting the efficiency or flexibility, you are basically losing the general trend or general state-based advantage. Whenever you are going for the state-based advantage, you are basically losing that flexibility, that there is no reason to actually open your communication channel or set up your communication scenario for all the time. So that's why it is very difficult. It is a challenging task in embedded domain. That is the main challenge in embedded communication. And maybe that is the difference between the general communication and in embedded communication. Okay. So this is now whenever we are talking about any embedded, many communication protocol. Before that, maybe I don't know how many of you actually have any idea about any basic networking course. So just to go by basic, whenever we are thinking about any communication protocol, First, we have to forget about embedded communication first. For any communication protocol, we have to think what we are actually expecting. Okay. So this is for embedded. We will come later. We will discuss it later throughout the rest of our class. But before that, whenever you are talking about any communication protocol, sorry. So what should we expect? Protocol means we are setting up rules. Now the question is, for on which of the topics I should set the rule. Okay. First thing, so here are few bullets that may guide you that whenever thinking about communication protocol, what points or what topics you should consider that will give the measure, that will give the details of that communication protocol. First one is, this is called the associated with physical layer. What does it mean? That means whenever you are sending a data from here it is an example shown from host A to server, any node to node. First thing is that, of course, that message should be divided, maybe some amount of bits you are sending to transfer that message from sender to receiver. So what is the typical bit size, or maybe in physical layer, the most important thing is how you are representing that bit. In which maybe that is maybe related to some voltage level, some high one, maybe some +5, 0, anything. But the main idea is your bits, your message should be represented by some bits 1, 0, and that 1, 0 should be mapped to some voltage level. Now today we will take one example in CAN where we will see that this is not that like some high voltage I can map to 1 or some low voltage I can map to 0. It is not always that. Due to some practical reason, that is not the case. But the main thing, first thing you have to know that, okay, this is my protocol, how my bit is getting represented, by which voltage level. Next, for that, whenever we are coming to that physical layer, basically these two are quite connected, these 2 or 3, that what are the signals incorporated, how to represent my bits, what are the signals incorporated, what are the signal strength of that, and those are handled by, this is called physical layer. I will come to these layers what we mean by these layers later, but just at this point you should understand that whenever we are talking about this bit related information, bit related representation of message, that is handled in the physical layer. Next question is, from my protocol I should understand that whenever my source is sending some data and some server is sender is sending some data and receiver is receiving, so they should be at a particular pace, they should be at a particular state, so that the receiver should understand, now sender has sent the data, now I am in a position to accept the data and work on that data. Otherwise, if maybe some sender is sending the data continuously and the receiver is accepting, but it doesn't know from where it should start operating on that data, that means there is no meaning to that data, and the processing related to that data cannot be performed in a proper way. So that means from the communication protocol we should expect the information that how my sender and receiver should come in should come in sync, we should say, should be synchronized, so that the proper communication should be started. So this is basically how maybe I can see these first 3, it is related to how my message should be represented in form of bit and in terms of signals. Number 1. Number 2, I should expect from my protocol should give me some idea that how my sender and receiver should be in sync. Here you can see this is a simple handshaking protocol that is given to make this host A and the server to take them in sync. Like host A is sending a synchronization request, server is receiving, and the server is actually sending another synchronization request along with some acknowledgement that yes, I have received your synchronization request and now I am in sync with you, and you also get synced with me. So this is sync. And then host is again sending the acknowledgement, and then that indicates that both this host and server, whoever may be the sender and the receiver, they are in sync and they are going to start some communication. So from that from any communication protocol, we should expect that. Third one is bus arbitration. That means this is just one, maybe in a dedicated bus scenario, if there is a dedicated link, dedicated communication between one sender to receiver, then that is not a problem. You know, when both are in sync, whatever data one sender is sending, it is going to a particular receiver. But we will see some scenario where a single communication bus is present and multiple nodes are connected. So in such scenario, when maybe this sender is sending and the sender is again also sending, so who will get hold of this bus? This is the bus, and from these multiple nodes, who will be the taker of the bus? Who will be the control? Who will be the taker who can actually take the control of the bus? Okay, so that point we have to understand from our protocol. Next, the fourth one is device addressing. Device addressing means, this is again I'm telling, that is not a problem when you have one dedicated communication like this, A to B. You are A is sending, B is receiving, and a dedicated connection is there. There is no problem of addressing. But when this is something like this, multiple nodes are connected to some shared medium. So in that case, how, when this maybe this node A1 is sending to B1, maybe this is B1, and not to the, maybe C1 or D1. So maybe one communication taking place to A1 to B1. So how this A1, so how that destination address should be assigned, should be given, that information should be given, so that this B1, C1, D1, each of them will understand that okay, this message is not for me, this message is only dedicated to B1. Or the same way for any communication, this is required. Next one, of course, these are quite standard, that whether the communication is wired or wireless. If there is wireless communication, then there are some added technologies, and how you are actually going to, what is the size of your data lines, how much size you will actually allow depending on your available bandwidth, depending on your performance requirement, everything. So those are data lines. So whenever maybe we will be in this class, we will be discussing just one protocol, maybe that is the CAN protocol, and also some dedicated communication protocols maybe next day. But later on, whenever you actually get to know any communication protocol, any communication, any CAN, after that maybe FlexRay, maybe MOS, you will see the protocols basically having some added features, or they are actually different in few terms, whatever bulleted in this slide. Mostly these are the few terms you are going to expect, you are going to question, so that you can understand, to better understand what is the difference between one protocol to the other. So whenever we will also discuss, we will also one by one take these points and we will check what happens in CAN. Okay. Okay. So again, these parts, whenever another types of classification is when you have intra-system protocol and inter-system protocol. Of course, as the name suggests, this inter-system protocol means communication established between two communicating devices. And actually we will take these USB, UART, these communication protocols next day, and we will see what are the features of them. So today I'm not going into that. And another one is intra-system protocol. Intra-system protocol is when communication you are considering between some circuit board within a particular board, or within a master component, some sub components are there and their communication you are considering. And today, among this intra-system protocol, we are taking this CAN protocol and we will be discussing in detail. Because CAN is having very typical features that is that is the reason it is leading a few embedded domain nowadays. Maybe automobile is one of the domain and few other domain also. We'll also get some idea about I2C and SPI next year. But today we will mostly focus on CAN. Okay. So before going to the CAN idea of CAN, just one conceptual framework. Okay, before that, I just want to know. Okay, from all of you, that most of you, do you have any prior knowledge, or have you done any networking course before?
No, ma'am.
Most of you.
No, ma'am.
Okay. So in that case, this is the very basic concept, or what to say, of networking. Okay. OSI layer. This is the first fundamental thing. But when we will see when for our embedded system, I will tell you why. We will mostly focus only these part. Okay. I will tell you later why. But first, for that, just understand that what does it mean by this open system interconnection or OSI model. This model typically divides your networking concept in different layers. Okay. What does it mean? Forget about embedded system as of now. Just think about general communication. Let's say we are also now through this Microsoft platform, we are also communicating. So what happened? In our case, we are actually running one application. Maybe I'm running this Microsoft based application. You all are running some software. You are all through your internet, you are running some application. Through that application, some communication is getting connected, and my system is basically connected with few other systems to this IIT network, right? So whenever some message is coming from your part to my part, what ideally should be, this is a very layman's example, but I think that will help you to understand from the very basic, that whenever some message is coming from your part to my part, first what you have to identify, you have to identify in which network my system is present. First thing. So first thing you need to know in which network the system is present. Now when you are coming inside a network means you can connection of maybe multiple nodes connected together and they are forming a network. When you are coming inside a network, then you have to identify within that network which node means what is my system. That means there should be some ID associated to my system. That is, maybe you consider some node ID. Okay. Now, when I'm talking about IIT network, there are multiple networks and they together are forming this internet. That means intranet, then internet, there are different levels. They are just names, but the basic concept is multiple nodes forming some smaller network. You are moving from smaller network to bigger network, some clusters to bigger clusters, and then you are identifying the system. So for that, to identify the system, first you have to understand in which network you have to go, in that, then you have to understand within that network, what is my system, maybe that is my node, but which node you should send the message. Again, in your system, if you see that there are different ports, but for different functionalities. Like some HTTP port, maybe when you set proxy, you have seen TCP port. There are different types of ports for different functionality. So that port, in which port, through which port your communication should come into me. So there, if these three things are mostly known, maybe your message can come. You can give these proper address for these three parts, which network, then within that network which node, and for that particular node which, what to say, which port. Then your message should properly come to my system, right? To this, the my system, and to this it should be give, I mean, it should come in this Microsoft related application. That means here some application is actually generating the data that you are wishing to transfer. That now, whenever you are some different applications are generating different data, it is not that always they are generating in the same way, same format. Of course, that is not possible. Okay, so that data should come through a particular layer that is called the presentation layer, that is making the data, whatever you are sending from your application proper, to be communicated to the next layers. Okay, next is session, that there should be a proper session to be established between these networks, these nodes, so that your data should come from your part to my system. Okay, and then when we are talking about this transport layer, basically now, since you know that you have the concept of a node, you have a concept of a network, and you have a concept of a port, now I think this is easy, that you have generated some data from your application. There should be some way to properly present that data. There should be some way, you are in the presentation layer, there should be some way where some session should be established. And I mean, there should, to maintain this dialogue, then you should identify, there should be some way to identify the port, the network, and the data link. Okay, data link means node to node communication. So this data link is mainly for node to node communication. Network means this gives you the routing information, how you will route to a proper node to the network. And this, I mean, network to network routing information, sorry, this is node to node routing information, and this is port to port communication, how from your port that information should come to the another system present in some other network. So this is the fundamental requirement where of these typical layers. And then finally, whatever communication is taking place, it is of course in whatever form you can represent. Maybe you are sending stream of 10, 10, 10, etc. But that should be mapped to some particular bit level, some voltage level, some I mean practical signal level. So those things, this bit representation and signal representation of your data, whatever you are trying to send, that can be handled by this physical layer. Okay, so these are that's why these are the typical functionalities of required to maintain your networking system. And these typical functionalities, it is divided into these typical layers. Okay, but think about some embedded system. When we are talking about embedded system, in embedded system, forget about these terms now. I will tell you later, not today. There is physical and data link layer. Basically, we focus only in these part because mostly when embedded system was developed, or you can think about Prior to IoT, cyber physical systems, isolated cyber physical systems, like it is taking some data from a sensor and it is sending some multiple nodes, and those multiple nodes are communicating. Okay, there was no concept of this networking and then port communication, etc. So at that time, initially, nowadays, when you are thinking about exposing your cyber physical system to IoT, of course, there is some concept of this network layer, transport layer, and everything so on. But what I'm focusing, typical embedded system, one isolated embedded system, there the communication is only required for, communication focus is typically in this physical and data link domain. That means only you are focusing in some node to node communication. You have to send data from one node to other, and that data should be represented by some means, some with some 1-0 representation, and those 1-0 representation or high-0 representation, and those high-0 representation should be managed, should be represented by some signal level. So that is the functionality of physical layer, and data link layer manages how from one node to another node that data should travel. And if there is there are multiple nodes, they are trying to send together. So how that collision, the possibility of collision, can be handled? That is the functionality that is taken care by data link layer. That's why we are telling that whenever we are talking about embedded communication, embedded system communication, we are just focusing on these two layers. But actual communication requires these 7 layers, mainly these 7 layers actually. And that's why OSI, this model, which is a main basic conceptualization of networking system, that typically incorporates all these layers. Okay. So this is now we will go to CAN. Here we will see how actually why we are talking about this node communication, and how we are answering this few typical questions that we thought that we should get these answers from this communication protocol. Okay. So this is how one controller area network or CAN network looks like. Now, maybe you heard about CAN, I don't know. In automobile domain and these type of domain, CAN is nowadays a very common name. Now, initially, when CAN was not there, if you think about different nodes of your smart cars, like smart cars, your nowadays your window is a smart window, where the seat, wherever you are sitting, if you do not put on the seat belt, then there is some sensor that will detect, and that will give you some sound. So that is also one smart node. The media, whenever you are actually playing some song with your USB or with your CD, whatever it may be, or some FM direct update coming from your internet, so that is also another node, another ECU. Generally we term them ECU, or just consider them as a node. So smart node, all they are connected, and these connections, initially before the concept of CAN, it was like this. Every node was connected to every node. See, all the connections were this. Now you can understand that managing these type of communication is very difficult, right? Another thing is that if you consider that, okay, there should be direct communication, but I will keep one master controller. In that case also, when there is some real-time requirement, like your brake, your steering, everything is connected to some these type of nodes. That means when you are pressing the brake, that information should be percolated to other parts of your other parts of your smart car also. So these parts, you understand that is, of course, depending highly on some real-time requirements. So for this reason, that if you trust too much on some central controller, then that is very difficult. That should, and if that central controller is somehow compromised or some becomes faulty, then your entire system, entire functionality of your whole system will be jeopardized. So for that, you need to have some structure, some framework where if you have one node getting faulty, first of all, you cannot have any central controller. Number two, if some node is faulty, you have to just directly cut out the node from your framework so that the functionality, critical functionality of other nodes, that should not get hampered. So with all these ideas and much more, we will see CAN is equipped with some more improved features. CAN came into picture when there's a central bus of CAN, central CAN bus, and the different nodes are connected this way. So what happens when any node tries to communicate to any other node? Maybe this node 1 is trying to communicate to node 3, then it will send these data to this common bus, and then that message will be sent to node 3. Now in this scenario, there are few questions. First of all, how, whenever I'm sending some data to a common bus, how other nodes will come to know that this message is only for node 3 and not for others. Number 2, if node 1 is sending the data to this bus, at the same time node 2 is also trying to send that data to this bus, among them, how to choose who will send that communication, who will initiate that communication. Number 3, if some node becomes faulty, what is the process, how that fault can be handled, or is there any process that fault can be handled? So CAN is equipped with different features to answer these questions. Okay, we will see one by one. Now for first, okay, 1 second. Is there any questions so far? Let me check.
No.
If you have any question, just ask me to stop and ask me that question. Okay. Okay. So the first interesting thing of CAN, first interesting part of CAN is that when the communication is taking place, CAN uses two dedicated ways for communication. One is CAN high and another is CAN low. Now, the idea of sending two different bits, maybe you can think 1 or 0. Of course, 1 or 0. That should be defined by two different voltage levels, right? So this is not quite straightforward that it is like for by 1 I'm sending it is high, and for 0 I'm sending it just a low 0 voltage or something like that. CAN uses this CAN high and CAN low, where the differential of voltage is considered, and then the value of that voltage is considered as the value of the differential is considered or actually indicates what is whether it is high or low. What does it mean? Well, 2.5 volt differential between these two lines, that indicates CAN high. Otherwise, you can see here, if it is plus minus 12 volt, then that is, if the differential is such high, then that is called the recessive voltage. Actually, there are two terms you can use. One is dominant mode and recessive mode. So in dominant mode, or dominant voltage is this 2.5. This is basically there must be within this 1.5 and 3.5. So this small differential, this is the dominant mode of CAN, whereas plus minus 12 is the recessive mode of CAN. So whenever we are actually signifying, let's say 1 or 0, high or low, this is not a straightforward one voltage. This is the differential of values of two voltages. Why? This is purposefully done to avoid the effects of inductive spikes. Now what happens in general communication, presence of such spikes, sometimes they flips the bit. Due to this spike, maybe there is a change in voltage level, so that whenever the receiver is receiving the value, I mean whatever sent from sender, there is some distortion in the voltage level, and receiver actually understand the reverse value. Maybe if sender has sent 1, receiver is understanding that 0, or vice versa. But to reduce that effect, the sensitivity related to this inductive spikes, this differential voltage concept was introduced in CAN. Okay. The second one is, okay. Next thing, as I mentioned, when we are talking about any embedded communication protocol, we are mostly considering the data link, that means node to node communication, and the signal level communication, what is happening. So in case of CAN, if you can see, the usual OSI model communication, that concept is not followed. Here the layers are different. Layers are, first one is physical layer. Of course, that is required, that we have already told that signal level and bit level representation is required. And the data link layer, there are the functionalities are divided into two layers. One is object layer and one is transfer layer. In object layer, the main purpose is message filtering and the status handling. And in transfer layer, there are few main functionalities, how this communication is taking place, that is fault confinement, error detection, etc. I will not name them now. Actually, we are going to detail them one by one. Okay, so let's start. So this is the details about CAN layers. Let's start about how you are actually sending the data from a sender node to a receiver node. Remember what we have drawn initially. We have this type of one CAN bus, and in that CAN bus, multiple nodes are connected. Okay. If that is the case, that means when this node is sending data to any of them, sending something to CAN bus, then that is sending the data in a particular form, and that form we are telling as data frame. That means in that data frame we are having some particular message and some added fields. We will see why they are required. Okay, just 1 second, just a minute. 2 minutes, I'm just coming back. 1 second. Okay. Sorry. Okay. Let's continue. Okay. You can see the slides, right?
Yes, ma'am.
Okay. So, okay. Now, with when we are sending, I mean, when any node, any CAN node is sending the from one node to other, that means the data, whatever data they are sending, there must be a particular form in which the data should be represented. So that is called the data frame. Now we will see how this data frame looks like. I mean, what is there in that data frame. First, start with this. There is a particular bit that signifies the start of frame. Next, first of all, why the start of frame is required? When the receiver will receive these data frame, it will actually receive multiple. Everything is 1 0 1 0 combinations. Whenever receiver is receiving this particular form of bits, it will understand that this is the start of frame. So this is mainly used for synchronization. Remember when we talked about that what we are going to expect from any communication protocol, there we talked about the handshaking. But handshaking, if you think that in each and every node, if you have to do this handshaking, that is very costly in this type of intra-system scenario. Inter-system scenario, when you're just communicating between the nodes of a same system. So there, if you every time send a signal, I send a synchronous signal, then the another node, each and every node will send you some acknowledgement. Again, you will send the synchronous acknowledgement. Then the communication are going to start. Then there is huge loss in terms of timing. So that's why this is the synchronization bit. That is the start of frame. Next one, this is the arbitration field. That will indicate that, see, this data frame, one node is sending to this data bus. Now the question is, which node is going to accept it? Or again, when, as I told before, when multiple nodes are just sending the data frame, which one will get the priority? So this arbitration field will decide that. We will see how we are actually deciding the priority, etc. Let's go. Next one, this is the control field. This control field is to give the flexibility. When we are talking about CAN, next another point we discussed, if you remember, what to expect from our communication protocol, that is the data line or size of the data. So here, this control field give you that information, that how much size of data, because CAN field, you will see that this is very flexible. Flexible means within a range, any number of bytes you can actually send. So control field actually gives you the information that how many bytes are there, how many valid bytes are there in this data frame. So that whenever the receiver will receive this data frame, it will check this control field and it will get the information how many bytes are actually valid data fields and how many the rest of them to neglect. Next one is CRC field. Now this CRC field is related to error handling and error detection. So we will discuss this, how CRC helps us to error detection. So we will come one by one. Next one is acknowledgement field. Now this acknowledgement field means whenever these data frame you have maybe sent to sender to receiver related to this data frame, whenever receiver is trying to send the acknowledgement that data frame has been received properly. So then this few particular values receiver can set to arrange send this information to the receiver that okay, the data is received and it is acknowledged. And then again, a typical bit sequence to indicate that this is the end of the frame, so that receiver will also understand. So now this is the end of the frame. So next it will expect some interframe space. That means that is some gapping. And again it will expect some particular sequence, particular voltage level that will indicate that particular signal actually that will indicate the start of frame. And then the so on. That way, synchronization, for synchronization, the start of field and end of start of frame and end of frame, they are important, because that will give you the idea to the receiver that from where it will try to get the data, which are all the actual data bytes, which are actually which data information to be actually used for error checking, which one is for acknowledgement, etc. So this is the structure of data frame that is used in CAN. You will see later on, whatever communication protocol you study, you will see this is the basic framework. Only this type of fields, only the size of fields based on requirements, based on features added, they are different. But whatever communication protocol you think of or you go through in future, you will see some data frame information should be given. That will give the idea to both the sender or receiver what sender is sending, how it will actually say the values of these data frames, and how receiver will interpret that frame. Okay. Next is this is arbitration field. Arbitration field is, now we are going deeper. Okay, the start of frame, you understood that this is a single or 1 or 2 bit values to particularly a typical pattern to signify that is the start of frame. Then inside we are going to the arbitration field. We are going here, this one. So this is the arbitration field. In this arbitration field, this is the identifier. Okay. Now this identifier's length is 11 bit. For CAN, 11 bit identifiers are used. Now why these identifiers are used? See, if you can see, one immediate question I thought it will come, that in this data frame, it is nowhere mentioned that if the sender is sending data, which receiver should accept it, or for what is the destination address, because some sender is sending fine this, so their sender address may be not required. But how when this message frame is traversing, data frame is traversing through this channel, how the other nodes will understand what is the destination address of this frame. This arbitration field is typically in CAN, message is sent in the form of broadcasting technique. That means any node is broadcasting the message through this line, and based on the type of this arbitration field, all the nodes, they check whether that arbitration ID is actually related to them or not. If that, then it is destination's decision. Then based on that, it will either accept or reject the frame. Okay. So this is the identifier field, type of identifier field that will give the idea to the other nodes what type of message it is and whether to accept that message or not. For example, when any media related ECU is nowadays, maybe you have seen in the smart cars, you have some controller of the media related node in your steering. So whenever this is going on, this communication is going on between media and the steering, of course some message exchange is taking place. Now this message is also, we can think that it is going through some CAN, if it is going through some common communication channel, but that maybe that message is not something related to maybe steering, no, not steering, maybe brake. or maybe backlight controller, all the other nodes. So they will understand that what type of message is going, and based on that, they will either accept or reject it. So this is one functionality of this identifier field. But along with that, this arbitration field is very important for setting the priority that we will come next. Another one is remote transmission request bit. Okay. So this is the RTR bit, that is the part of arbitration field. This signifies that when maybe there are two nodes, this node the data transfer will take place from this B to A. This is A and this is B. The idea is the data transfer will take place from B to A. Only A is requesting for that to initiate that transfer. So that means this is the receiver is initiating the transfer, but actual transmission will take place from some remote node. So in that case, again, the setting of bit should be high. This RTR bit should be set high. Okay. So this is the main idea of arbitration frame. Sorry, I have to take a break. 1 second today. 1 second. Sorry.